Welcome back to ECE 442-542. Happy Engineers Week. If you didn't know this week is your week, I'm not sure they have a week for every discipline, but you guys get one. So just as a reminder of a couple of upcoming deadlines, you're going to have 2 homework assignments. The homework number 3 is due a week from tomorrow. And then exam number 2 is on the 12th of March. Today what I want to do is continue with our discrete equivalent discussion, and ideally we will finish up zero order hold equivalents. That's the idea. We'll look at a couple of other zero order hold equivalents in the, let's say, the classical way of deriving those, the pure integrator and the first order system model. Then we will look at how we can find zero order hold equivalents directly in state space, and for finding zero order hold equivalents, that actually might be the more effective way to do it in practice, is have a state space representation and allow that to do the number crunching. We will look at ways to perform that by utilizing the matrix exponential, and hopefully you're somewhat familiar with that, but we will define that and then show how you can factor different expressions to give you a more numerically nice way of computing that matrix exponential. If we have time, we will start getting into the other half of the discrete equivalence, which is to do, just given a transfer function, what happens when we take that C of S to a C of Z, not preceding it with a zero order hold. Here's where we were started before with discrete equivalence and the zero order hold equivalent in particular. We have a plant, G of S. We are preceding that with a zero order hold. And we derived this relationship if we want to find the capital G of Z, which is the zero order hold equivalent of this plant, G of S. We simply find now the Z transform of G of S with one extra pole, where that extra pole is right at the origin. Find that Z transform and scale it, or pre-multiply it or post-multiply it. We're going to be dealing with scalar transfer functions, so we can simply multiply by 1 minus Z inverse. And that will now give us our zero order hold equivalent. As a review, we looked at 2 of those last time. If our plant was actually, if our analog system was a pure gain, we went through the analysis and we found that if we now divide that G of S by S, or introduce one more pole at the origin, we need to find the Z transform of K over S. Doing that, canceling terms, we get our gain back, meaning the zero order hold equivalent of a pure gain is just a pure gain. Then we actually, and here's more than what we did last time, but we will now derive a pure integrator zero order hold, and we will look at a first order's zero order hold, but I wanted to just give those to you for completeness to begin the lecture. Last time we looked at the pure gain and the double integrator, or a pure mass system, or 2 poles at the origin. That double integrator ended up giving us 2 poles at the, basically the equivalent location in the Z-plane to the origin in the S-plane. S equals 0 in the S-plane corresponds to what point in the Z-plane? Z equal 1. And that's where our poles ended up for the double integrator, and that's where one of the poles, or the pole, will end up in our pure integrator, and then we will look at what happens when we do this first order. Again, these notes are available, so hopefully I'm going to kind of quickly just continue on beyond this and not maybe give you time to copy that down, but you can create your table or give yourself space if you want in your notes and then copy that down later is the idea. But here I'm just wanting you, and one thing to be clear on is we are not directly z-transforming k over s squared. We're taking the zero order hold equivalent, meaning we are preceding these g of s's with this zero order hold and then deriving the transfer function associated with that. And that's why I tried to give you this additional piece of information so that you're not confused with if you now see a z-transform table that includes Laplace transforms in a column structure next to it, they may not have this k over s looking like what I have in this particular table. And the reason is this is now the zero order hold equivalent table. I want to make sure that you're clear on that. Let's now start by looking at the zero order hold equivalent of a pure integrator. Meaning now we are looking at an analog system that's simply a gain k with a pole at the origin. And our g of z, by definition, if it's the zero order hold equivalent, it's now going to be this factor 1 minus z inverse, where z inverse is corresponding to that one sample period delay, the z transform of k over s divided by s, which really gives us k over s squared. And we could go into the table and try to find that, and if we do, we will end up with this z transform of 1 over s squared with a k multiplying factor giving rise to this kt z over z minus 1 squared. But if we now replace or rewrite that 1 minus z inverse as z minus 1 over z and perform the necessary simplifications, we end up with this zero order hold equivalent of a pure integrator where we still are keeping the gain. We have a kt over z minus 1. If we did that by hand, meaning instead of just doing this is that step, you could say is from the table, we simply find in the table this k over s squared, and that gives us this ktz over z minus 1 squared. If we didn't have that, or if we wanted to convince ourselves of that entry in the table, let's look at performing this a little bit more thoroughly, or what I'll say by hand, performing this z transform operation by hand. And to begin with, we actually need to do some preliminary work, or some preliminaries, which is we really need, or will need eventually, to find the z transform of this 1 over s squared, which we will find to be equal to tz over z minus 1 squared. And what I want to do is actually convince ourselves or derive that result. Where does that come from? So if we do this in a more lengthy manner, we're now starting with two poles at the origin, or a 1 over s squared, or a pure mass system with our g of s, and reminding ourselves of what this z transform is. We sample the inverse Laplace transform of the 1 over s squared expression, and then z transform that sampled sequence of points. That's what we said. This is what we agree to define that z transform operation by. We simply are effectively inverse Laplace transforming 1 over s squared, then sampling that time domain waveform, and then z transforming that sequence of numbers. That's the process that we have established. What's the inverse Laplace transform of 1 over s squared? Do we remember? What's 1 over s, inverse Laplace transform? Maybe pardon? That's the step, isn't it? That's a constant. So now we're looking at that integrated. So if we had a constant integrated, now we have a ramp, don't we? So now we're looking at this ramp that we are going to want to sample, and this is only true for t greater than, we're looking at this one-sided or causal sequence, and these dashed lines are now saying we're going to replace that little t with a sampled version, or letting t equal to nt. Or we now are looking at the z transform of nt for n greater than or equal to 0. That's really what we're doing, or trying to do, with this process. The z transform of 1 over s squared boils down to trying to find the z transform of this ramp. And the z transform of anything, and in this case it's one-sided, we're going from n equals 0 to infinity. It's simply the functional form of that waveform, which is in capital T. T is just some sampled period value. That's a constant, and n is really our index, and that's what's changing with time. This now gets scaled by z to the minus n. Since capital T is a constant relative to what we are summing with respect to, which is little n, we can factor that t out from every term, and we now have this sum from n equals 0 to infinity of n z to the minus n. And that was actually one of your pieces of one of your z transforms on the exam, which I was hoping you would just find that in the table and go and say, here is the z transform. But let's see where that table entry is coming from. And one way that we can do that, because if you look at this in terms of a series of terms, it's going to maybe look a little bit ugly. It may not be obvious what that actually results in summing to or becoming equal to. So let's look at an easier case, and that is with respect to a constant or a unit step. So from before, we have derived the z transform of a constant or of a unit step. So let's call that x sub 1 of z. That's this sum from n equals 0 to infinity of 1 z to the minus n. This is our unit step. And that sums to what? One over 1 minus z to the minus 1, or that ends up being z over z minus 1. Now, what we are trying to find is we are trying to find x sub 2 of z, which is this sum from n equals 0 to infinity of n z to the minus n. This is why we've done our calculus. How could we go from a z to the minus n to something that looks structurally like an n in front and a z to the minus n? How do we get an n out front if we have a z? Let's say we had t to the n, and now somebody says, oh, give me n t to the something. We differentiate. So what we're going to do is we're actually going to differentiate the left side and the right side term by term, or on the right side just differentiate with respect to z, and that will allow us to get this n popping out front in this sum. So that's the observation that we're making right now. Here is our observation that's allowing us to make this connection between the z transform of capital X sub 1 and capital X sub 2. We can introduce this n into the infinite sum expression by differentiating the infinite sum in our x sub 1 of z formula with respect to the variable z. That's the inside of the observation that allows us to find x sub 2 of z, or capital X sub 2 of z. Here's our setup. For what we want to do. We have x sub 1 of z equaling this sum from n equals 0 to infinity of 1 z to the minus n, and that's equal to this z over z minus 1, but I forgot my quotient rule for differentiation, but I didn't forget my product rule, so I'm going to form this quotient into a product. Whoops, so that I can now write that as z times z to the minus 1 inverse. And now I can do the differentiation of that. And really what I'm doing is I'm saying here is my, what I'll call my left-hand side, and here is my right-hand side. I'm going to differentiate the left-hand side with respect to z. I'm going to differentiate the right-hand side independently with respect to z, and then set them back equal to each other and try to then find a formula or an expression for this infinite sum with an n sitting out in front of the z to the minus n. That's the idea. Is that clear? Which one do we? Let's look at the left-hand side first. Here's our left-hand side, and we want to differentiate that with respect to z, which is this sum from n equals 0 to infinity of 1 z to the minus n. So that now we can actually, that differentiation is a linear operation, and that sum we can actually sort of keep it to the left, and now we want to differentiate with respect to z 1 times z to the minus n. But if we do that, we end up with, whoops, minus n, and then we can just reduce that z to the minus n by 1 less in power, and that's now the derivative of the argument of that infinite sum. And we can create something that looks a little bit cleaner if we start combining and uncombining different pieces. Let me separate that z to the minus n into 2 pieces. I'm sorry, the z to the minus n minus 1 into 2 pieces. The far right piece, z to the minus 1, is not a function of little n, so I can pull that out of the summation. The minus 1 is not a function of minus or of n, so I can pull that out, and I'm left with then the left-hand side, when differentiated with respect to z, is this minus 1, z to the minus 1, this sum from n equals 0 to infinity of n z to the minus n. And that's the piece that I really was hoping to find or to create. That's that unknown sum that I hope I can find an expression to equal that or be equal to that. Let's now look at what happens when we differentiate the right-hand side. We're pretty far along on the left-hand side. We've got what we want. That looks okay. So now the derivative of the right-hand side was this, with respect to z, of z times z to the minus 1 inverse. So that's the derivative of the first times the second, plus the first times the derivative of the second, and the argument of z to the minus 1 differentiated with respect to z, that's just 1, and I didn't write that down. But this now I can rewrite. I can factor out a common z to the minus 1 to the minus 2 power. And I now have a z to the minus 1 times z to the minus 1 to the minus 2 gives me the z to the minus 1 to the minus 1. And over here I now have a minus z from the second term. But in the brackets I have z minus z. That's nice. And so now I have this minus 1 times z to the minus 1 raised to the minus 2 power. And if I now equate the expression that I derived for the left-hand side and set that equal to what I just found for the right-hand side, I now have the left-hand side was a minus 1 z to the minus 1 times this sum from n equals 0 to infinity of n z to the minus n, and that's equal to this minus 1 z to the minus 1 to the minus 2. And I can cancel the minus 1s. I can multiply both sides by z, and that will now isolate that square bracketed expression. So that I now have this formula for this sum of a ramp type waveform in z to the minus n as its z transform. I now multiply the right-hand side by z and put that z minus 1 factor squared downstairs, and that's now the expression that I was looking for, which now allows me to find this z transform of 1 minus z to the minus 1 of k over s squared, which is what I was hoping to find somewhere. Wow. There. I need this 1 over s squared, and I found that I needed this for its z transform. And I didn't know what that was equal to, and now I do. So now if I go back to this, I say that this g of z is now equal to this 1 minus z to the minus 1 k times the z transform of nt, where now 1 over s squared is all that was inside that curly bracket for the z transform, and that Laplace transforms into t, and I replace the t with nt, or I sample that t, where it has to be clear that one of those t's was lowercase and one was a capital T. So little t was equal to n capital T. Or this now becomes 1 minus z to the minus 1 times k, summation from n equals 0 to infinity of nt z to the minus n. The t again is just a constant. I can pull that out from all of the terms. And that in square brackets is what I just derived a formula for, which allows me now to say I have 1 minus z to the minus 1 times kt, and I replace that bracket with what I just derived, which was z minus 1 squared. And remembering what that 1 minus z inverse looks like, if I write it in terms of z's and not z to the minus 1's, I now end up with, canceling some pieces, this kt over z minus 1, and that's now the zero order hold of a pure integrator. Or zero order hold equivalent of a pure integrator. So I get a little bit sloppy with the terminology, but that's the zero order hold equivalent of a pure integrator. And if we were looking at the pole zero diagram for that system, what would it look like? We simply have a single pole at z equal to 1, which is consistent with our pure pole, or our pure integrator in the S-plane. It had a pole right at the origin. So that's somewhat consistent with the S-plane or the analog system. Now that we have this transfer function, we can actually start to play with this a little bit. So we now have this g of z equal to, and I'm going to just forget the k so that I now have a pure integrator. Let me gain it by 1. Let me say k is 1. So this is now t over z minus 1. Isn't that what I had with k equal to 1? And that's now a transfer function of a system where I inject a signal U and I obtain an output Y, consistent with what this was in the analog setting. This was an integrator. So what's this going to look like in the discrete time case? Hopefully it will look like an integrator. So let's see if that's true. This now says if I now try to put this into a difference equation, I have z minus 1 times y of z. So I'm now just cross multiplying t u of z. That should be clear from exam 1 preparation. Or I now have z y of z minus y of z is t u of z. If I take that into the time domain, what do I end up with? What's z capital Y of z? And I'm going to suppress the t in the argument, but that's y of n plus 1. Where do I want to go? Let me say that's minus y of n is equal to t u of n. Or if I solve that for y of n plus 1, then I have this formula. One way to interpret that is, suppose that somebody, and I'm going to draw this in an analog form, but suppose that was the sketch of y of n. Maybe my points are really, really close, and so I can connect the dots. That's now my function for u of n as a function of time n. Now, what I'm going to call y of n is going to be the area under that curve up to time little n. Meaning, if I now go up to some time n and shade that, I'm going to say that this shaded region is y of n. So if I now say, well, if I go to the next time index, n plus 1, then this black and blue area with a little just black is y of n plus 1, isn't it? So this whole piece here with the black and blue is now y of n plus 1, but we can actually obtain y of n plus 1 by looking at y of n, the blue, plus t, that's what this length is. This is now our interval of time, or this is t, and if we look at this point is u of n. Now we just multiply little u of n times t. That gives us the area of that rectangle, and that area of that rectangle now, that little sliver gets added on to y of n to produce y of n plus 1. So we're really just adding up or finding the area under that curve u of n. And that all came, this difference equation came from this process of replacing or going from the analog pure integrator into a zero-order hold equivalent system representation of an integrator in a discrete time system, and then pulling that into the time domain. This is now just a way of numerically integrating some waveform or function u of n. And the area under that curve will obviously improve as we shrink capital T, as we make the sample period smaller. But we've now just shown that we now have a difference equation that allows us to perform this numerical integration. And maybe it's easier to multiply and sum versus having to compute this integral in the continuous time waveform. If somebody gives you a u of n, you can sample that u of n every capital T units of time and use each of those to form this area under that curve just by using that first order difference equation. Or you could think of y of n as sort of the memory in your system, and it remembers what happened up to time n, and now it sort of gets some new information, and the new information it obtains is this additional little piece of area to enhance the area under that curve up to the next time period n plus 1. Questions on that? I was hoping to really get further. That was supposed to be 10 minutes up to this point. So maybe we need to start moving faster so time dilates, right? So that we can have maybe an hour worth of everyone else's time, and we'll just have maybe 10 hours in here. Won't that be fun? Everybody bring a sack lunch or your dinner in a bag. All right. Now, what we want to do is fill up the next entry in that table that we started with. We have now completed the first 3 rows of that. We sort of went on the odd rows Monday. Now we're doing the even rows. And we just derived this zero order hold equivalent of a pure integrator. What we want to do now is derive this formula, which is the zero order hold of a first order plant. Meaning if you now had an RC circuit and you wanted to simulate that or put that into a discrete time representation, how do we make that happen? How do we produce that system? How do we end up with this expression? That's what we want to do, and what we will end up doing is partial fraction expanding this formula inside the Z transform before we start sampling that. And what's going to happen when we partial fraction expand K over S times S plus A? How many terms are we going to have? 2. And what will one of those terms look like? Something over S, right? And we just did that one. Now we'll have something else that will be something over S plus A. So if we find what that Z transform is, we'll be able to combine those to obtain this whole mess. Is that clear? So before we get into this, we have to do another aside, but really you've already done this, but I want to just make sure that we're all on the same page with seeing where all of these R's and e to the minus AT's are coming from. So let me just say this is actually from earlier or from before, but maybe now it will be even more clear, I hope, once we do it again. So what we want to do to begin with is actually find the Z transform of an exponential. Not the zero order hold equivalent of an exponential, just the Z transform of an exponential, which means we're trying to find the Z transform of 1 over s plus a. That's our beginning step. So if I said, okay, we've had a x1 and an x2, let's do an x3 today. x3 is, let's say that's the inverse Laplace transform of 1 over s plus a. And what is that? E to the minus at. That's one of our standards, right? So we should feel very comfortable with that. 1 over s plus a, inverse Laplace transforms to e to the minus at. That's a real pole at minus a in the complex s plane, if we wanted to think of it that way. We now want to find a sampled form of that, so that now we have this e to the minus at with t, little t, replaced with little n, capital T. That's all we're doing when we're sampling, which says that we now have e to the minus ant, right? A n capital T. A way to remember that. So we now have an ant somewhere. Got it. And we're trying to z-transform it. Ooh, it's going to get messy, isn't it? But we can maybe z-transform this, or we can now say, what's the piece of this e to the minus a n t that's actually varying? Just little n. All the other pieces are fixed, which means that we can rewrite that, knowing our math behind exponentials. We can rewrite that as e to the minus at to the n, but then we could say, you know what, that's just some number, r. Once somebody gives us an a, once we've picked the sample period, capital T, we can now compute a number, r, and that's now all we're doing is raising that r to the nth power. Meaning, some of the tables you might have keep continuing to have e to the minus a capital T, but you could just think of that always as r, or the radial distance away from the origin in the z-plane is another way of thinking of that. What are we doing? We're trying to z-transform this 1 over s plus a expression, but if we do this in all of its glory, that's just sampling e to the minus at for t greater than or equal to 0. But that's now this z-transform of e to the minus a n t. We're in Eller. I thought they would be considerate. Their business etiquette, right? We're engineers. We know how to be the etiquette part, right? Yeah, let's... Now, where was I before I was so taken aghast by the traffic by the doors? We have more than one door, don't we, here? If you've never come to class, you might want to attend class just to see the setup. I guess you've been here for the exam, haven't you? All right. So we now need to z-transform, or put that functional form into our infinite sum, and we are summing that from 0 to infinity. We have e to the minus a n t, z to the minus n, but we've now said that we could also think of that as e to the minus a t to the n, z to the minus n, and this piece, again, is just our r. And now that we've done that, we can actually, both of those are raised to the power n. If we realize that we have a z to the minus 1 raised to the n, we can combine all of those, and we now have this sum from n equals 0 to infinity of e to the minus at z to the minus 1 raised to the n. And what have we done before? We've said, oh, let's just call that x. Now we have this sum of x to the n, and we know how to work with that. We have a 1 plus x squared. That's this geometric series. And we know when that's going to converge when x is less than 1. So that we now have this sum from n equals 0 to infinity of x to the n. And that now equals what? Was that this 1 over 1 minus x? And when is that going to be 1 over 1 minus x? As long as x is less than 1. Is that right? So that now we have this sum, and we can plug in the other expressions. We have this sum from n equals 0 to infinity of e to the minus at to the n, z to the minus n. That's equal to 1 over 1 minus whatever we called x. E to the minus at, z to the minus 1. And that's true as long as e to the minus at, z to the minus 1 is less than 1. That's when it converges. So that we now know, did I start calling that something? Let's call it x sub 3. So that I now know that capital X sub 3 is equal to, and if I multiply by 1 in this expression, where 1 is z over z, I end up with z over z minus e to the minus at, and that's true as long as e to the minus at over z is less than 1, or as long as the absolute value of z is outside this radius r defined by e to the minus at. So that we now have found that the z transform of 1 over s plus a is equal to z over z minus r for z bigger than r, and r is this e to the minus at. That was our background information, and we've already derived that several times, but I hope now it's even more clear when we start talking or start seeing these e to the minus at's. Oh, we could think of that as just an r value. Now we're ready to find that fourth row of our zero order hold equivalent table. We now want to find the zero order hold equivalent of a first order system, which we can then write as this k over s plus a. Our first order plan. Meaning we now have our first order plant, k over s plus a, preceded by a zero order hold, and we want to find what is g of z. And we've already done all of the necessary background material to find this answer, is the hope. What's the formula for capital G of z, just by definition? If this is the zero order hold equivalent, that's 1 minus z to the minus 1, z transform of g of s over s. That's our zero order hold equivalent expression. So this is now 1 minus z to the minus 1, z transform of k over s times s plus a. Now, what's the partial fraction of k over s times s plus a? Something over s plus something over s plus a. And you can find what that something is. Well, that something, in this case, if I just find it, is actually k over a over s minus k over a s plus a. So by a partial fraction expansion, we can now rewrite that product of terms in the denominator as individual pieces that we now know how to z transform. We now know that this is equal to z minus 1 over z times the z transform of k over a s minus the z transform of k over a s plus a. And we've now already found what the z transform of 1 over s is. We know what the z transform, we just derived that if we needed to convince ourselves again of what that was, so that we can now write all of these pieces down. K over a is just a scaling factor. And what's the z transform of a unit step? What's the z transform of 1 over s? And you can find that hopefully in the table if you don't remember it. That's the z over z minus 1. Then we just derived what the z transform of 1 over s plus a was. That was this z over z minus e to the minus at. Now, if we distribute this z minus 1 over z through both terms, the first term really gets reduced. It's just this scaling factor, or this residue that we were calculating for something over s before. We now have k over a minus the z's cancel in the numerator and denominator, and we have k over a z minus 1 over z minus e to the minus at. But if we put that k over a over the same denominator, that actually simplifies our numerator a little bit. We have a linear factor in z twice, but the coefficient is the same. One has a negative sign and the other's a positive sign. Those z terms cancel in the numerator. We have a k over az minus a k over az. Then we have a k over a times a minus e to the minus at, and we have a k over a with a minus times a minus 1. So we have a k over a minus a k over a e to the minus at. Let me factor out that k over a in the numerator. And we now have 1 minus e to the minus at. And downstairs we still have z minus e to the minus at. This is now our zero order hold equivalent of a first order system. And I hope that's the same expression that I had written down earlier in that table to begin the class with. This may look a little bit messy, but it's really not. Let's see what this actually tells. Yes?
So if we had a t, we did the 1 over s, we had a kt.
When we had a 1 over s, where were you looking at the 1 over s? Did everyone have their Dramamine? I'm scrolling kind of fast here. So this is a point that I hope we don't get too confused on, is this right-hand side is actually the zero order hold equivalent of these blues. So we really need the z transform of k over s. And that just gives us a k. Here, what we did when we started with this k over s, we're dividing that by s and finding the z transform of k over s squared. That gave us the capital T. I know, I didn't know how to really present this without maybe confusing you, but these are not the same directly as these. These are the zero order hold equivalent of those blue items. So if you take the double integrator and find the zero order hold equivalent, that's going to give you this expression on the right. Meaning, if we simply need the z transform of an integrator, not the zero order hold equivalent of an integrator, but if we just need the z transform of an integrator, that's just going to give us the k. And that's, I hope, what we ended up with here. Wow. So I needed to z transform this, k over a over s. That just gives rise to, when I do the factoring, just the k over a and the cancellations. Did that answer your question? So the question was, what happened to our capital T? And the answer is, it really shouldn't have been there. It wasn't there in this particular case because we were just concerned with the z transform of 1 over s, or k over s, or in this case, k over a over s. That's why you have to come to class, because I'm pointing at the screen and you're going, I don't know, he's just scrolling. I don't know what he's doing. Now, I said this will hopefully not look so difficult. What do we have here? How many poles do we have? We just have a linear term in the denominator, linear in z. We only have one pole, don't we? And where is that pole located? So now we're trying to find, or just sort of talk about this zero order, or this plant that's now a discrete time representation of an original first order plant. Our pole is where the denominator vanishes, and that's going to be at a value of z equal to e to the minus at. if we sketched that in the z-plane, where would that pole live? It's right over here in the right-hand side, isn't it? Less than 1. So now we have a pole right here at e to the minus at. What's the DC gain of this transfer function? So now, what's the DC gain of this? What's the DC gain of a g of s? How do we find the DC gain of a g of s? We look at DC, don't we? Or when omega is equal to 0, or when s is equal to 0. So we would find g of s, and if we went back to our original g, the DC gain of this system is what in the continuous time or analog setting? K over A. All right. Now, that's found, the DC gain of that analog system was found when S was equal to 0, at a 0 frequency, at DC. Now, where do we associate DC, or the origin, or 0 frequency in the z-plane? S equals 0 corresponds to z equal 1, doesn't it? So now z equal to 1 is really where we evaluate this transfer function to find its DC gain. If we look at this, g of z, and evaluate it at z equal to 1, what happens? The denominator becomes 1 minus e to the minus at, and that cancels that 1 minus e to the minus at in the numerator to give us a DC gain of K over A, just like our continuous time or analog system. So this is now a system with one pole, the pole living at e to the minus at, and a DC gain is found when we let z equal to 1 in that expression, and that's this K over A, 1 minus e to the minus at over and that's consistent with the DC gain in our analog plant. And we have a first order system in the discrete time, and we had a first order system in the analog time. So we really don't have, I mean, we're looking at a similar plant. It's just we've changed domains. We've gone from a continuous time to a discrete time setting. But we're getting equivalent type dynamic representations. Is that okay? Now, what if I, on an exam, say, okay, now you know how to get all these zero order hold equivalents. What if I said, give me the zero order hold equivalent of a state space representation? And we all know that I could give you up to a 12th order state space, right? That's what we've sort of agreed to. That's the maximum that I'll give you. Well, you can make it look easier if you just draw it in a block diagram, right? You can just say x dot is equal to ax plus bu, y is equal to cx. I'm just going to drop the direct feed through term because a lot of times we don't have that anyway. And I might just say, there's S sub 1. There's my state space representation, and A, B, and C or just whatever they are. If it's 12th order, what are the dimensions on A, capital A? What's A look like in terms of its shape? It's a square, isn't it? And what are the dimensions of that square? It's 12 by 12 if it's a 12th order system. And if I have one input, what are the dimensions on capital B? Has to be 12 rows tall, doesn't it? It has to be the same, compatible with the x dot. The x dot, the left-hand side, has to equal the right-hand side. So we know B has to be 12 tall and only 1 wide, because that's the only input that we have. And if we have one output, what are the dimensions on C? If we have one output, Y is a 1 by 1 matrix, isn't it? It's a scalar. And we need the product of C times X to give us a 1 by 1. X, we know, is already 12 tall and 1 wide. C has to be 1 by 12. All right, so we have A, B, and C. My 6th grade teacher, that's when I learned my ABC. She'd be proud. Took me a while. All right. You guys were in calculus at that point, and I'm just learning my alphabet. Here's our zero order hold. Or how could you do this? If I now give you a state space representation, what's one approach? You go out and buy a $150 calculator and do the transfer function from your state space, right? And you say, not a problem. Just a minute, my calculator's still going. It's 12th order. But it's in there, just wait a minute. Which means what? What does G of S look like? It has the same structure, and I think we've derived this, maybe not, but it's the same structure as G of Z if we go from state space to transfer function. This is SS to TF if you're texting. That's our state space matrices into a transfer function. And even if it's 12th order, this is going to be a scalar transfer function. What's the power of your denominator? What's the highest power of S downstairs? S to the what? $12, right? You have 12 eigenvalues, you have 12 poles. So you have S to the 12th, and so you're still writing, but you now know how to find a zero order hold equivalent. You could say, oh, I know what G of S is. It's just a 1 by 1 transfer function. G of Z is now 1 minus Z to the minus 1, Z transform of G of S over S. And now I simply replace that G of S with that big mess right there. And I have a way of finding it, right? Now my partial fraction expansion will have 13 terms, but you can do it, right? Because you've introduced one more pole at the origin, and you had 12 to begin with in G of S. Now, that's probably not the best way to do it, but it is a way to do it, and it's the best way maybe if you're doing it by hand, if I give you a 2 by 2 or a 3 by 3 system matrix A. But if you now are working and somebody gives you a 5th order system, you go, oh, let me find the state space representation, and I'll give him a state space zero order hold equivalent, and I'll keep the states there. Here we've buried the states, haven't we? Now I've just given you a g of z, a transfer function description of your zero-order hold equivalent. A better state space approach is as follows. It's to basically work with the given state space representation. So here's what we would do. Here is our state space in continuous time. So I should have done this continuous time state space so that if you're texting, it's CTSS. This is now x dot of t equaling a x of t plus b u of t, y of t is equal to c x of t. Now, do you remember what the solution of that is in terms of A, B, and C in the time domain? Have you ever seen that solution of this representation? X of t. X of t, and now I'm just going to assume that we will find the solution from some other time t0. So I'm going to assume that you know the state at that time t sub 0, and you know the input u of t from t0 on. Then to find x of t, it is e to the a t minus t sub 0. And remember, a could be a 12 by 12 matrix. So now we have this matrix exponential. Hold on. So e to the a t minus t naught is a 12 by 12 matrix that gets multiplied on the right by a 12 by 1 vector, x at time t0. But that's just the initial condition response. We forced it with u right there. We're driving it with u. We're shaking it with u. And what happens when we have an input to a linear system? If I want the output, what do you typically, or what would you say if you were in a 320 class and I said, here's a system, it has an impulse response h of t, an input u, what's y? What's the word I'm looking for? Convolution. So now I have to do a convolution with matrices. Here's what it looks like. So it's now plus this integral from the time that we started, which is t naught, up to the time that we're interested in, which is t, e to the a t minus tau. Remember, we have to flip and slide. So we have this matrix exponential, e to the a sigma, and we have to make one of these arguments, t minus tau. Then we have the input matrix B, u of tau, d tau. That's the solution. You could verify that that solves that differential equation by differentiating that and seeing that it satisfies x dot equal ax plus bu, and it does. But all we have to know is that this is now our solution, and now we have a way actually to discretize this particular system. What are we going to do? We are trying to do a zero-order hold equivalent, which means starting at t naught, if we apply a u to our system, what do? We find what u is at t naught, and we hold it constant until we get to the next sample period. One time step later, capital T units of time later. What we're going to do is we're going to say, okay, t naught, let's just make that some point in time, maybe little n cap t, and this cap and this little t, let's make it one time sample period later. That's now n plus 1 times cap t. This u of t, what's it going to equal in that one sample period interval? It's going to be fixed, isn't it? It's being held at 0 with a 0 order hold. It's just going to be u at time t0. If it's constant, we know how to handle it when it's integrated. We can pull it out of the integral, can't we, if it's a constant. B, we're assuming these are time invariant pieces. B can factor out of that integral. And we're really just going to end up with this matrix exponential integrated. And what happens here? We're just going to have e to the a, and these two, the difference between t and minus t naught is just one sample period, capital T. So this t minus t naught is going to be e to the a, capital T, where capital T is a scalar. I don't know, I may just do this over the weekend and post it. We'll see. I don't know if I want to pick up here on Monday, or I may just give you something to watch. In case you're having trouble sleeping, you can watch it, okay? So we'll figure out where we go from here. Stay tuned, but keep your eyes and ears open.